These are the techniques which are used for both signal analysis and signal synthesis. The first technique is discrete Fourier transform, which is abbreviated as DFT, while the second technique is fast Fourier transform, abbreviated as FFT. These two techniques are the most widely used signal processing techniques, which offers its applications not only in DSP, but you will find their applications almost everywhere. So we will start from DFT and we will learn how DFT can be applied on a given time domain signal to obtain its spectrum. Then we will perform its computational analysis and we will conclude that DFT is computationally very slow. So in order to develop a faster version of DFT, we will need FFT algorithms. So FFT is not a new technique or a new transform, it's just the optimized implementation of DFT. So any algorithm or a family of algorithms which will implement DFT in a faster way or in an optimized manner will be called FFT. So after discussing DFT, we will discuss FFT algorithm and we will also perform its computational analysis, and finally we will compare the performance of both DFT and FFT in terms of number of computations required for the calculation of Fourier transform. In this animation, you can observe four rotating phasors which are rotating at four different speeds, and correspondingly we are observing sinusoids of four different frequencies. So sinusoids are nothing but simply the projections of phasors, and the frequency value of sinusoids depends on the speed of these rotating phasors. So as you can see, the blue color phasor which is moving at the slowest speed, so the corresponding sinusoid is also the lowest frequency sinusoid because it is taking highest time to complete itself. While in the case of purple color sinusoid, which is the highest frequency sinusoid, in this case, the corresponding phasor is moving at the fastest speed. So the frequency value of sinusoid basically depends on the speed of these phasors. Similarly, the amplitude value or the peak value of these sinusoids are depending on the radii of circles formed by these rotating phasors. So the highest the radius of a circle, the highest will be the peak of a corresponding sinusoid, and vice versa. Now, if you will observe the additive effect of these four sinusoids with respect to the time axis, then the resultant signal would look like this one. So the resultant non-sinusoidal signal is simply a composition of these sinusoids. And as we discussed, sinusoids are simply the projections of rotating phasors. So we can also say the resultant complicated looking non-sinusoidal signal is made up of four rotating phasors which are rotating at their own speeds. So frequency analysis or Fourier analysis of signals is also called phasor analysis, because if we want to analyze the non-sinusoidal signal, it means we have to figure out what particular rotating phasors are present in it. Now let's take a look on both time and frequency domain views of a given non-sinusoidal signal. Basically, this is a 3D diagram, or this diagram has three axes. The time axis, which is indicated by a dotted line. The second axis is the frequency axis, which is this one. And the third axis is the amplitude axis, which is this one. Now, the signal which is given to us is non-sinusoidal signal. And according to Fourier, this signal or a non-sinusoidal signal is nothing but simply a composition of simple sinusoidal signal. So this signal is equal to summation of these three sinusoids having a different frequency value, which is represented by f1, f2, and f3. And the corresponding amplitude values are represented by a1, a2, and a3. So if we want to observe these sinusoids with respect to the time, then our point of view should be in this direction. If we want to observe the signal variation with respect to this dotted line axis, then we are required to look at these signals in this direction. So can you imagine what particular signal will appear in by looking at these signals in this direction? Since all three sinusoids are varying themselves with respect to the time axis, so they will overlap with each other. And if we will add them together, the resultant signal will look like the resultant signal, which is this one. And how this signal is obtained, suppose this is the t naught time value and the corresponding amplitude is this one. So how we have obtained this amplitude at time t naught? It can be obtained by summing the corresponding amplitudes of these three waveforms at time t naught. If you will add the amplitude values of these three sinusoids at time t naught, you will get the amplitude value at that specific time instant. Similarly, we have to follow the same procedure in order to obtain the signal. So the resultant signal which we will observe with respect to the time axis is this one. But this signal is considered as the complicated looking signal because we cannot tell various things by looking at this waveform. So what we want to do, we want to observe our signal information in frequency domain rather than the time domain. So we have to change our point of view from time domain to frequency domain, and for that purpose we have to change our point of view by 90°. So if we will look at these sinusoidal signals in frequency domain, our point of view should be in this direction because we want to observe with respect to this axis, so we will look in this direction. So how these sinusoidal signals will look like, you can simply imagine a whole sinusoidal signal will be covered by a single vertical line, or the whole variation pattern of a sinusoidal signal will be covered behind this single vertical line, which is so called a spike. And this spike will appear at f1 Hz frequency value because the frequency of this sinusoidal signal is f1. And the height of the spike will be equal to the amplitude of this sinusoidal signal. Similarly, this sinusoidal signal having f2 Hz frequency value will also appear as a spike at f2 Hz, and the third sinusoidal signal whose frequency is f3 Hz will also appear as a single vertical line or spike at f3 Hz. So what we are observing here, every sinusoidal signal is appearing as a vertical line or a spike in frequency domain, and the spike will appear at the frequency value of a given sinusoidal signal. So we'll observe this kind of a spectrum. So the representation of a time domain signal in frequency domain in terms of these spikes which are present at their specific frequency values is so called spectrum. Now somebody could ask, why do we need another domain representation when we already have the time domain representation? Isn't the usual time domain representation enough for us? So the answer is frequency domain representation is usually considered as the more simpler representation of our signal because it offers several advantages which we could not have by looking at our signal in time domain. The first advantage is if it is required to develop a mathematical expression of this signal, then we cannot do it by looking at this waveform. So what we can do, we can first split the given signal into its ingredients, then we can write a mathematical expression of this signal in terms of its ingredients because we already know the mathematical model of a sinusoidal signal. So this is the first benefit to represent our signal's information in the frequency domain. The second benefit is, suppose we are required to tell what is the exact contribution or strength of second harmonic component present in a signal. So if we will just look at this waveform in time domain, we can never answer the required question. So we will first need to analyze the given signal into its sinusoidal ingredients, and then we will look at those sinusoidal components in frequency domain. So by observing the height of a spike, we can tell the strength of a second harmonic component. So by looking at signals information in frequency domain, we can easily tell the strength of each and every harmonic component. So this is the main advantage or the most important advantage of observing signal information in frequency domain. Another important advantage of frequency domain representation is the signals spectrum helps us to describe the effects of certain systems. For example, we have an electric filter which is designed to pass a certain range of frequencies, and it is designed to reject another range of frequencies. So if we will apply this signal to that electric filter and observe the filtered output at the end in time domain, so the filtered output will be another non-sinusoidal signal which will be different from this one. So by looking at the time domain representations of signal at the input and output of a system, we cannot tell what particular frequencies have been retained by our system and which frequencies are rejected by our system. So if you will take the signals spectrum both at the input and output side, then we can conclude what frequencies are retained by our system and what frequencies are rejected by our system. So suppose if this is the spectrum of our input signal which we have applied at the input of some filter, which contains three components f1, f2 and f3, and let's assume we have also calculated the spectrum of our output signal which contains only one spike at f1 hertz, and the output spectrum doesn't contain these two spikes. So we can simply conclude system characteristics like our system is designed to reject these range of frequency values. So frequency domain representation of signals also helps us to describe systems characteristics. So this is another important benefit or advantage to observe signals information in frequency domain. These are some important points from the previous slide, which you can read. In a time domain, we observe a composite signal and we are unable to see its ingredients by looking at the resultant signal directly. So we have to change our point of view and we have to observe our signal from the side, where each sinusoidal signal will appear as a spike at its own frequency value, and that representation of signal in frequency domain is so-called signal spectrum. And the most important advantage to observe signals spectrum is we can quantify the strength or the contribution or the amplitude of each ingredient, which is the main objective of performing signal analysis. If you can remember, we have already discussed this thing in earlier slides. The main objective of signal analysis, we have to find two things: what frequency components are present in our signal, and what is the exact contribution or amplitude or quantity of each sinusoidal component. So this is all about the frequency analysis of signals. Now let's conclude the lecture on this animation. Suppose the complicated looking signal is this one, which is represented by red color, and it's simply a composition of various cosine and sine waves. And if we will look at the ingredients of this signal in frequency domain, every sinusoidal component will appear as a spike. So the description of a signal in frequency domain is so-called signals spectrum, where the height of each spike will represent the strength of each sinusoidal component present in a given signal. So if you have any difficulty in understanding these concepts, then you can ask your question in the upcoming live session. Thank you very much.